Sorry, let me again. It was not possible to.
When you are ready, Jonas, just say that we can start, so also
yeah.
it can be recorded.
So now, now I can switch.
Now it works. Yep, I think we are ready. So I think we can switch the recording on.
Okay, yeah. Thank you very much. And I would also like to thank the organizers for inviting me and for giving me the possibility to speak here about partial wave analysis. My original idea was to speak about our activities, which are related to coupled channel analysis, but there was a wish to hold it in a more general context and to speak about experiment partial wave analysis. However, it matches very well with our activities because we are also using data from different experiments. And therefore, I will also show some examples of our activities here. Okay, first of all, a short introduction. I will start with a short introduction and would like to motivate why coupled channel analysis with different data, with data from different experiments are so helpful. In this context, also the description of the dynamics is very important. Before then, I will come to the coupled channel analysis of antiproton-proton data of these three channels here, together with pi-pi scattering data. And in this analysis, we have also found interesting 1- spin exotic 1- wave. And therefore, we extended this analysis by adding also compass data where also this wave is, has been seen. Finally, I will also show some partial wave analysis with gamma-gamma reaction. So we have already heard a lot of things in the morning session today. And here we are using real gamma and used to obtain parametrizations from the dynamics from the other fits. And finally, I will give a summary and a conclusion. Okay, first of all, we have concentrated our activities so far on the light meson sector. Therefore, a few words related to this. So the light mesons are, as you know, bound states consisting of U, D, and S quarks, and they cover the non-perturbative QCD regime, as you can see here. And from the theoretical side of view, it's the description is very challenging, and one has to make use of lattice QCD calculations, for example, or phenomenological models. But also from the experimental point of view, it's very challenging because one has to deal with many overlapping resonances with same quantum numbers. One has the resonances are decaying in different channels. And therefore, also the distinction between conventional QQ bar mesons and exotics are also very difficult. So a very important point is therefore the access to the inner structure of these objects. And one important characteristic is, of course, the production mechanism. For example, we have heard this already also today, that, for example, gamma-induced processes include QED effects, and therefore the calculation is very can be done very precisely. And this gives really a very proper access to the inner structure. On the other hand, also exotics with gluonic content should mainly produce in gluon-rich environments like radiative JPAC decays or central production or antiproton-proton annihilation. While on the other hand, they should weakly couple to gamma-induced processes like gamma-gamma fusion. And also the characteristics of the decay pattern is very important and helpful. One example is that the gluons should decay flavor blind, part of the phase-space vectors, or molecules should decay into meson pairs close to threshold. So all in all, to summarize this, it is very important to determine in a very precise way the pole parameters and especially also the coupling strengths of the production and decay systems. And these are really the essential key points in order to categorize the different resonances which one can see. Therefore, an analysis of a single channel is not sufficient, and it is then really needed in the most elegant way to perform couple channel analysis, and this with data from different production mechanisms and different decay systems. And one advantage, or there are a lot of advantages when one compares this to single channel fits. Namely, one can use a common and unique description for the dynamics, which is often not possible by only using a single channel fit. One can also describe thresholds effect in a really better way. And in addition, one can also fulfill the conservation of unitarity in a better way. So we have also heard a lot of things related to this during this workshop. And one has also more constraints due to common amplitudes if they are there. Okay, one essential key point is the description of the dynamics. I don't see here the topics. Okay. This we have also heard here during the workshop. The Breit-Wigner functions widely used, and of course this is a good approximation for isolated resonances appearing in a single channel. But however, the Breit-Wigner functions violate unitarity, and the extracted resonance parameters are not unique and are dependent on the production and decay process. So this is really a very big problem, and therefore it is in a lot of cases needed to make use of more sophisticated descriptions, because resonance is decaying in general in multiple channels, and they appear also several resonances with the same quantum numbers appear in the same channel. This is also a problem, and when, for example, a resonance is located at the threshold, also the line shape, so the Breit-Wigner-like line shape will be distorted. And therefore, one can use, or one should use, approaches with an adequate consideration of unitarity and analyticity. And here one can, for example, make use of K-matrix, N over D method, for example, or also two potential decomposition. Now it's, it's switching. Okay, one important point here is, of course, the analyticity. And in our partial wave analysis, we are using the K-matrix formalism. Therefore, a few words related to the analyticity in the K-matrix. Yeah, the K-matrix, so the scattering process can be described here with this equation via the K-matrix. And if you, for example, would like to analyze different channels here, for example, antiproton-proton annihilation, where a resonance is produced with a recoil particle, then one has to introduce the P vector or also the F vector, and can therefore, with this approach, describe also those processes in addition. In the past, the K-matrix, or often the K-matrix, has been used with standard phase-space vectors in the very past. And here, this is a phase-space vector, as you can see here. And the disadvantage of this standard phase-space vector is that this violates the constraints of analyticity. And one point is, for example, that this produces unphysical cuts if the decay products have unequal masses here, MA and MB. So this can be seen here in this histogram. This is an example for the eta prime channel. When you are here above the threshold, everything looks fine. This is here the normal behavior of the phase space vector. This looks fine. Then if you turn to the below the threshold, then the real part gets imaginary. Then this looks also fine, but at a certain point, the sign is changed here below the square root again, and the imaginary part gets real again, and this is then completely nonsense. And if you then compare this eta prime channel with the pi channel, and you project, for example, all the things to pi, then you get really wrong results. And this can be solved by replacing this normal phase-space vector by, for example, Schuh-Mandelstam functions, which consider the analyticity and also the continuation to the below the threshold in a proper way. Okay, for our partial wave analysis, we are using this the Pavian package, which we have developed, partial wave interactive analysis software. So far, antiproton-proton annihilation, E+ E- annihilation are supported, also gamma-gamma fusion, and also pion-proton and pi-pi scattering data. It is a user-friendly package where one can, for example, define and hypothesis and also other settings via flat ASCII configuration files. One can, for example, here switch between different formalisms. One can also use different dynamics. Pavian is based on an event-based maximum likelihood fit. One can use event-based maximum likelihood fits, and the standard minimizer is Minoid2, but it is in principle flexible enough to switch to other minimizers. Parallelization is supported, and there are also some additional analysis tools for extracting, for example, the pole positions or the branching fractions. And one can also generate events based on the model which one has obtained. One can do some histogramming things, and efficiency correction can be also done. Now I will come to the first analysis which we did in the past. So this Krishna will give a talk on next Monday about the Panda experiment, and also hear a bit about these investigations, also a bit more. But we have also observed some interesting additional results which I would like to present today. As a reminder, Crystal Barrel was operating between 1998 and 1996. It was a fixed target experiment, and Crystal Barrel has investigated antiproton-proton annihilation at rest and in flight. And the physics program was, of course, a spectroscopy of light mesons and the search of exotics. Yeah, these are the three channels which we have investigated here: pi 0, pi 0 eta, pi 0 eta, eta, and k plus k minus pi 0 at a beam momentum of 900 MeV, together with pi scattering data. And the motivation was here to measure in a precise way the expected resonances A0, A0, A2, F0, and F2, of course. But also we tried to look for the spin exotic pi1 wave, which has so far only seen in antiproton-proton data at rest. And therefore, this was also an idea to look into. And all the analysis here is based on event-based maximum likelihood fits, and was by taking into account really the complete phase space with amplitudes from the initial state down to the complete final state. Okay, an interesting channel here is, of course, this k plus k minus pi 0 channel. And here just a few words concerning this. When one tries to analyze this channel in a single channel mode, then it is in principle completely impossible. This is impossible to disentangle the isospin 0 and isospin 1 component for resonances decaying to kk, as you can see here. So the decay angular distributions are the same, and so we have in principle no chance to disentangle this. But by performing a couple channel fit and by adding, for example, the channel pi eta and pi eta, so both channels have a well-defined isospin component, then it is, of course, possible to disentangle the A and F resonances also in the KK mode, because here in this case, you can share the relevant initial amplitudes, and therefore then you have directly access to the individual isospin components. Okay, and in addition, we are using pi scattering data. And what is the advantage? So as you know, scattering process is only characterized by the elasticity and the phase motion. And this gives then really a very good and easy access to all the resonance properties and to the resonances which are contributing there. And this means also that also the phase shift and the elasticity is properly taken into account also for the antiproton-proton data, which are fitted simultaneously. And therefore, and available for this measurements and also theory data from isospin 0 SD wave and also for the isospin 1 P wave. And this gives, of course, good constraints here for the individual waves here. Yeah, for this analysis, the best fit result has been achieved here with this K-matrix descriptions. For example, for the F0, we have used 5 poles and 5 channels. For the F2, 4 poles and 4 channels. And also here for the pi1 wave, we have used here description with 1 pole and 2 channels. Yeah, but in addition, we have also used 2 Breit-Wigner descriptions for the phi and K star, but these are really isolated resonances where is it, I think, allowed to do it. This is a fit result. These are only examples of mass projections here. So again, we have fitted the complete phase space simultaneously. But here one can just a demonstration that the fit can describe the data very well. I don't want to go into more detail here, but an important point is here that we have observed here in this pi eta channel also very significantly the pi1 wave, this spin exotic 1 minus plus contribution here with more than 60% contribution. This is a fit result with scattering data, so I don't want to show all the figures here. This is just an example for the phases for the 3 individual waves here, and one can see that the scattering data, the phases can be described very well. And here you can also see how many data, different data has been used for this. Yeah, and this gives really good constraints here. Yeah, once one has the results, so one has fitted the data very well, it is then also possible to extract the resonance parameters because the K-matrix contains all resonance parameters. For example, the masses and the widths are defined by the pole position in the complex energy plane of the T-matrix on the sheet closest to the physical sheet. Here is one example. Here, this is for the this is a relevant sheet for the F2 wave with 4 resonances which we could identify. Here, for example, then here this here is the F2 1270. By projecting the pole position here to the x-axis, one can extract the mass. By projecting it to the y-axis, one can extract the total width. But in addition, it is also possible to extract the partial widths by calculating here, by extracting here the residues around the poles. With this method, it was possible to extract more than 50 different resonance properties for the individual resonances here, F0, F2, A0, A2, and ρ. But I don't want to go into detail here, but what was also an interesting observation was, of course, here this 1 minus plus wave, and here a few words to this. So this 1 minus plus wave has been seen here with in the decay pi 0 eta in the channel pi 0 eta. And again, we have used here a K-matrix description with 1 pole and 2 channels, pi eta and pi eta prime. And this was a bit motivated by the JPAC analysis where with compass data. In our case here, for this analysis, no data for pi eta prime were available. So we have only used this channel due to unitarity reasons. But the result is in principle very interesting because here when one look into the phase difference between the pi1 wave and the A2 wave from the T-matrix, which we have obtained. So this is a fit without any compass data, but when one compare this with the compass measurements are here the red points, the phase shift between the pi1 and the A2. And here the black shape is the obtained phase shift of our fit. So this is really in a very, very good agreement, as one can see here. Yeah, and we have not fitted the compass data. This is completely independent. And by the fit, and we could obtain here a pole position of 1400 MeV for the pi0. And this is in principle in agreement with all other measurements in the PDG so far with, for the spin exotic wave decaying into pi eta. Now I will briefly come to the JPAC analysis. So they have analyzed also in a couple channel mode, the 1- plus and 2++ wave of the compass data for the channels for the decay into pi eta and pi eta prime. And the motivation was in principle the following. So in the PDG, there are in principle 2 pi1 hybrid candidates listed below the mass of 2 GeV, namely one at 1.4 GeV, which has only been seen here in pi eta, and one around 1.6 GeV, which has been seen in pi eta prime, but not in pi eta, and also in some other channels like rho pi, B1 pi, or F1 pi. Most of the parameters, not all, but most of these masses have been obtained here with the Breit-Wigner fits. And from the theory side, only one hybrid state is predicted slightly below 2 GeV. And the JPAC analysis used the N over D method by taking into account in a proper way analyticity and unitarity as well. Here, these are the data from compass, and one can clearly see here this peak at 1.4 GeV in the pi eta spectrum and the 1.6 GeV in pi eta prime. And this is a result. So the JPAC analysis could reproduce the data very well. So one can see really a very, very good agreement in all mass spectra and also in the phase difference between pi1 and A2. And they have described the data only with one pole, only with one pi1 pole, and they obtained here a mass of around 16 MeV. And here, with this one pole, it is possible here to describe here this peak at 1.4 GeV and here this peak in 1.6 GeV. Yeah, so this demonstrates very impressively that it is needed to go beyond Breit-Wigner descriptions, because this is completely impossible to describe these two peaks here with one Breit-Wigner function. Yeah, so then this is really a very, very good example to make use of such more sophisticated descriptions. Yeah, since we have also observed this pi -1 wave, we have therefore also added the compass data to our fits and fitted this simultaneously. And this is here the result. We can also reproduce all the compass data very well. The only difference is that we have not used this N over D method. We have also used this K matrix here. But we can also describe the data only with one pole scenario. And this is the result here for the antiproton-proton channel in pi. So the data can be described very well. And here this yellow shapes here describes the pi1 wave contribution. We could also then extract the masses and the widths and also the coupling strengths of the pi1 wave. And this is also, yeah, I don't know if this is a suppression, but then here so here in this analysis, we are also taking into account this pi eta prime channel with the compass data. And the thing is that then the pi1 mass is moving really then from 1.4 GeV to 1.6 GeV. And this is then what we obtained here, pole position at 1.6 GeV with a width of around 400 MeV. Okay, then I will come to gamma-gamma reactions. We have also analyzed gamma-gamma channels by making use of the parameterization which we have obtained here with this fit, which I've presented before. And these are the channels here, these three gamma-gamma channels, which we have analyzed in a coupled channel mode, pi-pi, kk, and eta-eta. And here again, the advantage is that one can here, by analyzing the kk bar channel together with pi-pi and pi-eta, one can disentangle here the F0 and F2 resonance parts. Yeah, again here for the F2 and F0, F2, A0 and A2 waves, we have used this obtained K-matrix parameterizations for the dynamics. And this gives really so good constraints that it is therefore possible to get proper access to all the gamma-gamma bits. Here, this is a fit result. Black represents the data, and red the fit. And one can see here that the fit can describe the data very, very well. So this has been done by Maike Küssner. And here in color, here the shapes represents individual contributions. But here one can really see that the data can be described very well by this fixed parameterization. Yeah. And with this result, it was then possible also to obtain the gamma-gamma bits. This we did with an extraction of the pole residues of the F vector, which you can see here. These are the 4 poles, for example. This is an advantage for the F2 scenario. And here by extracting the residues here around the pole, it was then possible to obtain the gamma-gamma bits. And this results really in a very accurate measurements for several resonances here for masses below 1.8 GeV. One example is here the F2 1270 here, where one can see when one compare here this result here with the other measurements, one can see that the uncertainties are really very low. Yeah, in addition, it is also, for example, first determination of the gamma-gamma bits for the F2 prime for the 2 helicity scenarios separately. Yeah, so it was impossible to disentangle also the helicity 0 and 2. This was already discussed also today in the morning session. And this is in principle for all spin 2 resonances, it was possible to obtain the gamma-gamma bits for the 2 helicity scenarios. And the future plan is here to perform partial wave analysis by adding, for example, the radiative JPAC decays, and to compare directly the production strengths of gamma-gamma with radiative JPAC decays, which then gives really a lot of information related to the inner structures. Okay, to summarize, the determination of resonance parameters and coupling strengths to the different production and decay processes are an important key point to classify the states. And this can be done by performing coupled channel analysis of data from different production mechanisms and decay systems. It is needed to describe this with sophisticated descriptions of the dynamics, where one should also take into account analyticity and unitarity. And I've shown here some examples with antiproton-proton data, gamma-gamma fusion, pion-proton scattering data, and also pi-pi scattering data. And I've shown here that the peak here, for example, at 1.4 GeV in the pi-eta system and at 1.6 GeV in the pi-eta prime system of this spin exotic 1- plus wave can be described by only one K-matrix pole. And therefore here, this is really a good example where Breit-Wigner parameterizations are not working well. Thank you very much.
Thank you very much indeed for this impressive and very convincing plea for highly sophisticated multi-channel analysis. Yeah. Are there any questions to Bertram? Christoph, go ahead.
Hi, Bertram. Thank you very much for this very nice overview. I have a question regarding the mass range around the A0980, F0980. Is the data you are currently analyzing sufficiently accurate to get access to the A0, F0 mixing?
Oh, good question. Which data do you mean? So in principle,
Well,
the anti-proton
on page
data.
11, you mentioned that
I
you
think
can disentangle the iso vector and the iso scalars.
Yeah. So
And
I think
gamma, the same can in principle also emerge, right?
yeah. The problem is, so the number of events is not so large here. These are around, I don't know, at least below 100,000 events. And I think this is not enough to disentangle all these things, because the A0980 contribution is not so large here, as one can see here. There's a complete A0 contribution, for example. But I have the impression, so one needs a lot of statistics, and I think when, for example, Panda will start, this is so with in a high luminosity mode. Then I would guess, I'm not sure, so one has to calculate it a bit. Then I would be sure that one should be sensitive to this mixing scenario. But here I think the number of data are not enough.
That would be cool. And then on page 16. I was a little puzzled by your sheet label. You write there first sheet.
Yeah. Oh, sorry. Second sheet is the next one to the physical. Yeah, the
Okay.
second sheet. Sorry. Yeah.
Thank you very much.
This is, of course, here. This is this relevant sheet. Sorry. Yeah, you are correct. Thank you.
All right, Pat, and then Claudia afterwards.
Hi, thank you.
Yes.
Sorry, go on, Claudia. You can go first.
Okay, Claudia, go first.
No, I think I didn't see Patricia. So, Patricia, go ahead.
Thank you, very kind. So, thanks for your talk. I just get a little bit puzzled when you presented the K-matrix model, because I think this is a slightly different K-matrix model that I am used to. So, if you can.
Yeah, maybe I have. To be more precise, I have also some backup slides where it is maybe becoming more clearer.
That's fine. But when you present the P and the F vector that you are going to use, yeah, exactly. So
this one, okay, here this is standard phase-based vector. So
okay, now I see. No, that's standard.
So the point is that here the P vector contains in principle the same pole parameter. So these are the same poles as the K matrix, as you can see here. This is an important point. And the K matrix can contain here also some background terms, as well as the P vector here.
Yeah, but you are only freeing the parameters. So your parameters in K are fixed, and then you're only freeing the parameters in P, or you free them all?
For the first fits, which I've shown here with anti-proton data and with scattering data, here the G factors are the free parameters, of course, and we have also used, I think, here an energy-dependent background term in the zeroth order. And for the P vector here, this is here then for the gamma studies, all the G factors are then fixed with this parameterization, as I mentioned, and only here this part of the production, this beta is the production part, is then only fitted. For example, for the gamma data, which I've shown. And
this will include all the KK bar, meaning charged and neutral contributions, right?
In principle, yes, all channels, and yeah.
They are mixed up, so we can. Yeah, thank you.
Okay, Claudia, now.
Yes, thank you. I have two probably stupid questions. The first one is, do you really have event-based likelihood, so you need to sum on all events? You do not have a bind.
Yes. It depends. Yeah.
For a high luminosity experiment, it could be a problem. I
Yeah.
believe. Is it in the plans?
Yeah. So at least here for this analysis, what we did here for the antiproton proton data, we have really used a complete phase space. So all informations so here we have here, as you can see, we have also fitted the decay angular distributions. So in principle, this is a fit of all dimensions. While for the scattering data in pi and also here, as you can see here for the compass data, which we have added, so we have no 4 vectors for it. It was not possible to do it in the complete phase space, so we have only used here this extracted waves. So this is really a combination of binned data and really event-based data. Yeah. You are right. When one has a lot of data available, then maybe the computing time is rising when you perform here an event-based maximum likelihood fit. But then one has to think about how to improve this situation. Maybe we think about this also to handle with large data samples, also with this event-based maximum likelihood fits.
The second question, you also already sort of mentioned it, the fact that you are not likely, for instance, in Panda, you are not likely to have a full phase space acceptance. How do you?
Yeah, but in Panda we have in principle the full phase space available, and this is the advantage for the partial wave analysis, and this we would like.
Yeah, of course. How sensible are you to the fact that in most cases the data that you will analyze later will not have the full space coverage?
Yeah, but for the Panda data, this will be available then, because this is a detector for pi detector, so the complete angles are covered. So therefore, it is impossible, and we are and Panda will measure it exclusively. So it is possible to perform fit in the complete phase space.
In all the region of energy or energy?
Yeah. Okay, maybe there are some slight holes, probably, but here with a fit here with event-based maximum likelihood fit, it is then also possible to extrapolate it. Here maybe here this is one good example here for the gamma channel here. Here in the outer regions, here these are the decay angles here, from the production. One can see that the efficiency is very low or is going to 0, but this can be covered then in principle in a more or less good way by the fit itself, because the individual waves have then characteristic shapes there, especially in the outer regions, and this can be then covered. But for Panda, it is really then the case that in principle the complete decay angles are covered. This should be possible.
Okay. Thank you.
Okay, Sören.
Yeah, hi Bertram. I had a question about the F0 1500. I think you can see it here on page 23 in the K plus K minus, the second peak.
Yeah, this is here in this case is more the F2 prime. F2 prime. So we have here in this case, so the F0 1500 is yeah, in principle, yeah, the production is very low, or one maybe. So this is a question one has to give an upper limit here with this data samples.
Okay, then I take back my question.
Yeah, because in gamma, so yeah, so it's a question if this is produced strongly in gamma, but this is here the F2 prime. This peak is really the F2 prime.
Actually, we have seen that in Bell, the 1500 in gamma also.
Okay, yeah.
It was included from the PDG, but I think we hadn't seen that.
Yeah. Okay.
But my question would have been, okay, I can ask the question. The pole position was always different for the 1500. It was seen in JPSI decays, in B decays, in gamma gamma, in PB bar, but the pole position has always been quite different. I mean, like 50 MeV, and I would have been curious what pole position you get. I mean,
yeah. As I mentioned, so we are using this K-matrix formalism, and with this, it is impossible to have a unique pole position. This is only for all the data which we are analyzing with the same K-matrix. We have in principle the same pole position there, and so the shift of the peaks is only then related to the production process, which has been taken into account then properly, or also to the decay process. And in this case, we obtain in principle a well-defined pole position for all data, or even when the peaks are somehow shifted. This is in principle here. This is really a very, very good example here for the pi1. Yeah, you have here the pi1 here, the peak here in pi eta, which is seen at 1.4 GeV. And in pi eta prime here in 1.6 GeV. We can calculate, so we can describe these data here only with one pole. So there's really one unique pole for the pi1. And this can then describe the data here in these two channels. This is not possible when you are performing the fits with Breit-Wigner shapes. Then you can see it by eye. You need two Breit-Wigners here. One Breit-Wigner for the pi eta, and the other one for the pi eta prime. And this is then the advantage to make use of this K-matrix formalism. So this is really then a unique property, and the physical property. Yeah. And this is the problem that in principle these peaks here are shifted depending. Strongly, sometimes really strongly, depending on the production mechanism.
Yeah, yeah.
And therefore, when you only see the intensities there, then you can see it. This is automatically possible that you can see some shifts when you look in this channel, or in this reaction, or in that reaction.
Okay, thanks.
Okay. Let's have one final question. I'm aware we are running a little bit out of time, but I mean, it's worth it, I think. But let's have one final question from people.
Yeah, I think I will ask the long one in the discussion session. Okay. So I just had a quick question of on slide 24. Sorry, I missed. You said that this was presented earlier in the BEST talk. I probably missed it. So this determination of the different widths for the two helicities of the 1525, could you explain that a little bit?
Yeah, we have used in our fit. We have in principle fitted the different helicities individually. So we have waves with helicity 1, helicity 0, and helicity 2. And with this contributions, and which is then in principle here related to this p vector thing here, this beta here. This is then in principle individually fitted for helicity 0 and helicity 2. And then you can extract the residues for both helicity scenarios individually. Mm-hmm. This is in principle then what we did here. And so we did really a complete partial wave analysis, and then therefore one can disentangle these two helicity components. And yeah, as we have heard, this gives also a very interesting and good insight into the objects.
Okay, let's discuss this later
okay.
Okay, well, thank you very much indeed, Bertram, and everybody who asked questions. Okay.